Okay, here we go. Question 1.1. We have americium 241. Nucleons? Well, we know that we have 95 protons, and the mass number at the top gives us protons and neutrons. So neutrons is going to be 241. Take away 95. That should give us 146. 1.2. Americium is produced by the decay of plutonium. So we can see that it's going from plutonium to americium. The mass hasn't changed, but the proton number has gone up. Therefore, we know that it has to be beta minus decay. We can say no change in mass as our reason. Then we're told the americium decays by emitting alpha. So let's get our americium. We know that's decaying into mystery nucleus X plus an alpha particle, which we know is a helium nucleus. So just thinking about maths, we know the proton number left is going to be 93 and 237 for the mass. Easy so far. What is ionization? When an electron, or electrons for that matter, from an atom or molecule. Now in chemistry, we say that there are such things as negative ions when you add an electron, but they don't really exist by themselves, but ions can, positive ions that is. So why isn't the americium in a smoke detector that bad? First thing is that it's a very small amount used, but more importantly, alpha particles cannot penetrate the casing, or even a few centimeters of air, so poses no risk. So we have a force and extension graph. We're being asked to show where Hooke's law is not being obeyed anymore. We know that's the limit of proportionality. That's the end of the straight bit. So there's the linear mode, and then once it starts to curve after that, it's no longer proportional. It's not obeying Hooke's law. All right, and then we're being asked, how can we find out the Young modulus? Well, we know that the gradient from this graph gives us F over delta L. And if we take our Young's modulus equation, FL over A delta L, that means that this is our gradient. So all we need then is the length and the cross-sectional area. So obtain A by measuring diameter with micrometer, and then A is equal to pi d squared over 4. And then we can just say obtain original length L with ruler. Therefore the Young modulus is equal to the gradient times L over A. But they're asking us to draw the unloading curve after it's gone to that point there, A. It's a little bit mean because we don't know if it's actually gone past the elastic limit or not. It probably has, and so we can assume that it's not going to return to its original length. So therefore we just draw our unloading curve, or rather unloading line, just like that. It's not going to return to its original length, it just ends up there. And we're being asked to explain that, so we can say that wire has deformed plastically, so does not return to original length. And the second mark is a little bit mean. So yes, we've said that, but why isn't it a curve? Why is it a straight line? We can say that it's the same gradient as most bonds in material are unaffected. We still have enough bonds for it to actually return to its original length via the same route. It's just that the bonds that have been weakened, well, they're the ones that result in it deforming plastically. Not the best question ever. Not a fan of that one. Okay, so we have a cable that has diameter of 6 millimeters, so I'm going to turn that into meters. The Young modulus we're given is 2.0 times 10 to the 11 pascals. We're looking for the force necessary to produce a strain of 0.2%. And so that's equal to 0.002. So let's just say 2 times 10 to the minus 3 in terms of just a decimal. So we know that Young modulus is equal to stress over strain. We're not changing strain, but we are changing stress. That's going to be F over A divided by epsilon. In other words, F divided by epsilon A. And so therefore that means that the force is going to be equal to all of these things multiplied together. We're just rearranging it there. And let's do it all in one go. Let's times that by pi d squared over 4 for the area. So that's 2 times 10 to the minus 3 times 2.0 times 10 to the 11 times pi times 6 times 10 to the minus 3 squared divided by 4. Now you can either put that into your calculator, or we can actually tidy things up a little bit. We have 2 times 2 divided by 4, so actually that will disappear. And then we have 6 times 10 to the minus 3, so that is going to be, I'm just going to write this down here, 36 times 10 to the minus 6. Then we have times 10 to the minus 3, just taking that, times 10 to the 11 times pi. So sorting out our powers of 10, we have minus 9 and 11, so that's just times 10 to the 2. So that is 3,600, I do believe, times pi. Let's pop that into our calculator, and we have 11,309.7, blah blah blah. How many sig figs are we going to go to? Well, our data was actually given to 2 sig figs, so actually I'm just going to call that 11 kilonewtons. There we go, 11,000 newtons. So we're lifting a mass of 600 kilograms, so mass is 600 kilograms. We're looking for the maximum acceleration in order to have that strain. And so, well, we know the force from earlier, don't we? Let's just say that's 1.1 times 10 to the 4 newtons. So let's just have a think. Whenever it comes to lifting stuff, say with a crane, tension, or if it's a rocket, we need to think to hold, how much force do we need just to hold something up like that? What would the force in the wire be, the tension? The force would of course be equal to mg. But if we're accelerating it upwards, of course we need a bigger force. We need the extra force. So it's not only mg, but it's plus ma. We're looking for a, so let's rearrange this. Let's factorize first. So F is equal to mg plus a. Therefore, F divided by m is equal to g plus a. Therefore, the acceleration is going to be equal to the force divided by the mass minus 9.81. And that is equal to 1.1 times 10 to the 4 divided by our 600 minus 9.81. And using their number that they've used, 1.13 times 10 to the 4, that gives us 9.0 meters per second squared. But they've been naughty by giving the force to 3 sig figs there. What's even worse is that they should have then given the answer to 3 sig figs, but they've only given it to 2 sig figs. Not very consistent. Okay, so now we have doubled the mass. So what would we need to change in order to achieve that acceleration again? Well, we saw earlier that F is equal to strain times Young modulus times the area. We want the same strain, and the Young modulus isn't changing. Therefore, we can say that the force is proportional to the cross-sectional area. And we're doubling the mass, therefore F also doubles. Therefore, area needs to double. And we know that because area is pi d squared over 4, area is proportional to d squared. Therefore, d doesn't need to double in order to do that. It just needs to multiply by root 2. If d multiplies by root 2, then the area has doubled, which allows us to have that double the force. It does say changes, so we could also change the wire instead. Instead of changing the area, we could change the Young modulus. Use wire with E, that is a Young modulus, that is 2 times that of original wire. Ah yes, this question. Bit of Kirchhoff's laws. This catches a lot of people out. So first things first, we have currents going in and they result in one current coming out. So the first thing we can say is I1 plus I2 equals I3. Because of Kirchhoff's first law, we know that current can't just disappear. Current is conserved at junctions. Okay, so R1 is equal to 0, so basically R1 just disappears. So in essence what we have now is this circuit. We have our voltages, rather EMFs, resistors as well. So we're being asked to calculate what is the PD going to be across this 30 ohm resistor. Well, can you see that it is the only thing in this loop? From Kirchhoff's second law we know that if there's only one EMF and one resistor in a loop, then they must have the same PD across them. Therefore, V3 has to be 10 volts. Next we're being asked to find I2. Well, now we're going to consider this big loop. We can see that we have two batteries opposing each other. Therefore, we can say that the voltage is just 2 volts. That is the PD across the 10 ohm resistor. We also know that the resistance is 10 ohms. Therefore, just using Ohm's law, V equals IR, current is just going to be that voltage, 2 volts divided by 10. That gives us 0.2 amps. What happens if we increase R1? Not an easy question, this one, because we have to not only think about R2 but R3 as well. So let's think, if we now have a resistor in there, that means that that R3, that middle resistor, is going to get less of the share of that 10 volts. Therefore, V3 decreases. And so then if we consider this last loop here, then we can see that if V3 decreases, then the 10 ohm resistor is going to get more of the share of that 12 volts. Therefore, V2 increases. Not a nice question. This question, wowzers, it's caused a lot of discussion in the Discord server. People were very confused, and it is easy to get confused with this one because you think there's one thing going on, but it's actually not that at all. So we have the mass of the pellet, 8.8 grams. We have the mass of the block, 450 grams. And we're told that the block rises. We're going to have to find 0.6. We always do pretty much if we're given a height. So that's mgh. So that's equal to, well, it's not just the 450 grams because the pellet is in it as well. We do need to turn it into kilograms. So there's going to be 0.45. Now it's not 450 because the pellet is embedded in the block by the time it swings upwards. So we're going to say, oh, let's just say that's 0.459. Let's do it to 3 sig figs times 9.81 times 0.63. And that gives us a gain in GP of 2.84 joules. Therefore, we can say that the GPE of block at the end, that's the same as the KE of the pellet going in. We can say that, right? No, we cannot. And this is where people get confused. We have a collision going on. Whenever you see a collision, the only thing that you need to think is that we have conservation of momentum. It's only under certain conditions that we actually can say that kinetic energy is conserved in a collision. That's in elastic collisions. But elastic collisions, things are pinging off each other. If you have an inelastic collision, things couple together, they smush together. And that's what we have here. So this has to be an inelastic collision. We can't say kinetic energy is conserved in the collision. And even if you think there was, it's always best to say, well, it's a collision, so let's go with conservation of momentum first. So what can we do then? Well, we can deal with the lifting of the block first. So yes, we can say that GPE is equal to KE for the block and the pellet. Therefore, we can say that half mv squared is equal to mgh. M's cancel, so it actually doesn't matter how heavy the mass is. So yes, I don't actually need that bit up there, but if you want to do it the long way around, that's fine. So therefore, I can say that the speed of the block after the pellet has hit it is equal to root 2gh. And that gives me a speed of 3.52 meters per second. Now we can go into momentum. So we can say that we have a before and after, and we're just thinking about the collision now. So we can say that all the momentum we had before, the momentum is mass times velocity. So I'm going to say that's mass of the pellet times the initial speed of the pellet. That's ultimately what we're trying to find. And then afterwards, well, we just have the mass of, I'm going to call it the block, but we know that it is ultimately the block and the pellet, don't we? So these two things are equal to each other. So I'm going to rearrange this. The speed of the pellet before is equal to the mass of the block and the pellet times the speed afterwards, which we found from conservation of energy up above, divided by the mass of the pellet. So that's equal to, we can just keep it in grams because it's just conservation of momentum. So 459 grams times the speed that we had afterwards divided by the mass of the pellet. Let's go with 8.8. And that gives us 183 meters per second, seeing that our data is all to 3 sig figs really, even though they've given the answer to 2 sig figs. So there you go. What's the important thing there? If you see a situation that has a collision of any kind, you know you're going to have to use conservation of momentum at some point, even if you have to use conservation of energy in the question as well. So what would happen if it was a steel block instead? Well, the pellet would rebound, not embed into the block. So let's have a think. If it goes in compared to goes in and then comes back, well, we know in the latter situation, we have a greater change of momentum. Therefore, also the same for the block. Therefore, its speed would be greater. We can say kinetic energy is greater, therefore reaches a higher height. And it also has less mass too. It's lighter, so therefore it's going to have a greater speed afterwards. So which is going to be more accurate? Not an easy question, actually. Well, the steel method isn't going to be accurate, as you would need to know the rebound speed of the pellet in order to calculate change in momentum. In other words, impulse. And we can't really assume that it's coming back at the same speed as it goes in either. So we can't say that we assume that the final velocity of the pellet is just equal and opposite to the initial velocity of the pellet. That's because, well, if that happens, the collision would be perfectly elastic, but you can't really get a perfectly elastic collision. So it won't be perfectly elastic, and really it won't be anywhere close to elastic, because that implies that kinetic energy going in is equal to the kinetic energy coming out. So we're saying that no energy is converted into sound or heat or even light. No, in reality, we know we're going to get all of those out. So that kinetic energy is not going to be the same. So therefore, it cannot have the same speed rebounding as going in. We can't measure it, so therefore it's not going to be very accurate. Whereas the first method is fairly accurate because we know that it's lost all of that momentum. It's given all of its momentum to the block, okay, the block and the pellet. Okay, what is a step index optical fiber like? Well, we know first of all we have the core. That's what the light travels down through TIR, and we have our protective sheath on the outside. But in order for TIR to happen, we must have something in between, because whatever we have on the outside here, it must have a lower refractive index than the core, because that's one of the conditions necessary for TIR to happen. And we call that the cladding. And this is the protective sheath. Cladding must have a lower refractive index than the core in order for TIR to occur at boundary. Light travels through the glass core. How many marks? 3. Well, I would say that would be probably it, but they expect you to mention the fact that the cladding offers some protection. But that's not its main purpose, so I'm not a fan of that. Cladding provides protection for core from scratches, which could cause light to refract out. But that's circular reasoning, because if the cladding wasn't there, then it would refract out anyway. So yeah, bit redundant if you ask me. Okay, so what can we see here? Blue light has a higher refractive index. I'm just going to say N for shorthand. Therefore, it travels slower through the medium, through the fiber, because we know refractive index tells you how much slower light travels in a material compared to in a vacuum. Therefore, we can say that when the blue and the red light, part of the white light, are emitted, sent down the fiber, the blue light arrives after the red light, as it takes a longer time to travel. Therefore, we end up sending this, but we end up receiving that, because the red and the blue light are arriving at different times, like that, whereas before they were sent at the same time. So we can say the pulse has been broadened. And the mark scheme says that you should find the time taken as well, which I think is just completely unnecessary. That's dumb, because if you want to find the time taken, we know that speed equals distance over time, and the speed, of course, is equal to the speed of light in a vacuum divided by the refractive index. And you end up with times of 5.87 times 10 to the minus 6 seconds and 5.84 times 10 to the minus 6 seconds. Two changes that we could make. We could add a relay to resend fixed signal. We can also call these repeaters. We could, of course, use a monochromatic source. So just use one color. I mean, that makes sense, doesn't it? And we could also use a monomodal fiber. So in other words, it's only light that travels straight down that actually gets to the end. Not a big fan of those though. So how do we find the wave nature of sound? We should probably use interference. I would say 2 speakers with moving microphone to detect maxima and minima, therefore proving that it is a wave. Maskim says you could use diffraction around a door, but I think that's a bit naff personally. This would be a better thing to say. So we're being asked to find the time between seeing the flash and hearing the bang. So we know that speed is equal to distance over time. Therefore, the time is going to be equal to distance divided by speed, just swapping those two round. And so that's our 2,500 meters divided by the value of 480 meters per second. And that gives us 5.2 seconds. Do we need to calculate how long it takes for the flash to reach them? Probably not, because it's going to be very, very, very small. So in that vein, why do we have to make that assumption? So that we can assume light took no time to reach the observer. Oh, these are dumb questions. So how could we conclude that speed isn't dependent on frequency? If you hear a bang, that consists of multiple frequencies. It's not just one sound being made. And it's not like he heard one part of the bang, then another part of the bang, all arrived at the same time. So how was the value better from Borelli and Viviani? It's more accurate because it is closer to the accepted value that we know and love. Okay, finally, some non-wishy-washy stuff. So here we go. Speed of sound is given by this. So we're being asked to find a value for K. We have a temperature of 0 degrees C. That's nice and easy, so that just disappears. And we see that the speed of sound was 331.29 meters per second. Oh, look at this. We're going to 5 sig figs. Crazy. Therefore, K is equal to that speed divided by the square root of just our Kelvin value for 0 degrees. And that is, well, we need to go to 5 sig figs. So 20.045. And to finish off, some more wishy-washy stuff. How is a quantity accepted? Experiments are repeated by other scientists and values compared to previously published values. Thank goodness that's over. Let's go on to some proper stuff. Multiple choice. So the beryllium captures a proton, so it ends up becoming 10 and 5, but then it's giving out an alpha particle, so we know we're taking away 4, taking away 2, so we end up with 6 and 3. So it looks like it's going to be C. 8, comparing X-rays with UV. A, lower frequency. No, we know it's the opposite. B, no, they all travel the same speed. C, no, they're waves, so therefore they demonstrate all of those. It has to be D, but let's just check it. Electrons emitted have a greater maximum kinetic energy. Yes, because they have more energy. Oh, lots of words. So radiation is shone onto a metal. Okay, this is photoelectric effect. Second source, no electrons are emitted. What must be greater for A compared to B? It has to be frequency, because we know that E is equal to HF. So it has to be B. Easy so far. Okay, so we have two wires, different thicknesses. So which is correct? Is the strain going to be the same? No, because X is going to stretch more, so greater strain. B, is the stress greater? No, it's not, because it has a bigger area, so therefore it's going to be lower stress, because as we know, stress is equal to F over A. So if the area is bigger, the stress is less. C, the tension is the same. Yes, we know that to be true. The force is pulling the same on both. Let's just check D anyway. The elastic energy is less. No, it's going to be more because indeed it is stretched more. So it's going to have more energy. Okay, so we're being asked to compare energies for de Broglie wavelength. Right, we know that lambda is equal to h over mv being the momentum. Now, if we're being asked about kinetic energy, that's not super easy actually, because if we think about kinetic energy, it's equal to half mv squared. So actually we're being asked to compare momentum and kinetic energy. So let's have a think. So whenever a question involves comparing momentum and kinetic energy, what we want to do is take kinetic energy, multiply both sides, so we end up with half m squared v squared, and that is equal to half times the momentum squared if we place the bottom of our de Broglie wavelength equation with p for momentum. Therefore, kinetic energy is equal to p squared divided by 2m. I've just rearranged that. So if the kinetic energy is going up by times 4, then that means that the momentum has gone up by times 2. So if p doubles, then the EK quadruples, or we can think of it in terms of P is proportional to the square root of the kinetic energy. Maybe that would be even better. So if that's going up by times 4, momentum is going up by times 2. So if the momentum is going up by times 2, then that means that the wavelength is halving. So therefore it has to be B. Not as easy as it first appears. So when the pulses have passed each other, oh, well, that's nice and easy, isn't it? Because waves, yes, they do interfere, but once they've passed each other, they just go on their merry way. So it has to be C. So what happens to light when it goes from air into glass? Well, we know that speed changes. Speed goes down, doesn't it? But we know that they start bunching up as well. So if that's our glass, they start bunching up like that. So wavelength also goes down. Frequency stays the same. Therefore, the answer is B. It's speed and wavelength. So if we increase the intensity of light on the surface of a metal, then we are going to increase the work function. No, absolutely not. That's going to stay the same because that's a constant associated with the metal itself. The minimum frequency, no, that's the same as the work function, isn't it? C, is it going to be current? Yes, it is. Because we have more light, more photons hitting, therefore more electrons being released. It's not going to be D because, well, we're assuming anyway that by changing the intensity, increasing the intensity, we're not changing the frequency of the light, we're just turning the power of the light up. So therefore frequency isn't changing, so the kinetic energy of the electrons isn't changing. So they've drawn this a funny way just to try and catch you out, but if we just swap over the variable resistor and V, it's exactly the same circuit. So don't get caught out. First things first, what happens if R is decreased? Well, we know that the current is going to go up because the overall resistance has gone down. So therefore it has to be A or B. But then what's going to happen to the reading of the voltmeter? Well, if R is decreased, we have two resistors in series. The total voltage is being shared across them. Therefore, we know that its share of the PD is going to go down. So therefore, it has to be B. So which one is not equal to the EMF? Let's check A. The reading when the switch is open, technically that is true because there's no current flowing. So whatever the voltmeter shows, that is going to be the PD. So that's not our answer. B, energy changed to electrical energy when, yeah, we know that's true, isn't it? Because EMF is equal to, well, it's a voltage, so it's energy per coulomb. So that's right, so that's not our answer. Twice the reading when the switch is closed. Yes, that's also true because, well, we have a total EMF. If it's shared across two resistors that are R each, then therefore it's going to be split evenly across them. So therefore it looks like it has to be D. Let's just check it. It seems like it's the opposite to B. So energy produced when unit current passes. No, because we know that EMF voltage isn't joules per amp, it's joules per coulomb. So that is wrong. So that's our answer. Oh, great, diffraction grating. So we're going to have our wavelength. That's 4.9 times 10 to the minus 7 meters. We have lines per meter. So let's turn that into meters per line. Let's turn that into actual meters. So that's 1 divided by 6 times 10 to the 5. That gives us 1.67 times 10 to the minus 6. Let's just call that 1.7 times 10 to the minus 6, actually, because we don't need to be super accurate when it comes to multiple choice. The first order at 17 degrees, or actually, let's have a look at this. The first order at 17 degrees, the second order at 34 degrees. They can't be true, or one of them has to be false, because we can't have just N2 being double the angle of N1. That doesn't make sense. So that's a little shortcut there. So let's do a calculation. N lambda equals d sine theta. So if we're looking at the first order, then N just disappears. So therefore, lambda divided by d is going to give us sine theta. So let's put that in the calculator. We're going to do 4.9 times 10 to the minus 7 divided by our grating spacing. And then we're going to inverse sine that. And we end up with 17 degrees. So yes, that does make sense. If you check the others, you find that no, the second order is not created at 34 degrees. If our answer just now came out at anything other than 17 degrees, then B could be correct. But let's just check C as well. Third and higher orders, are they produced? Well, let's have a look. If we're looking for the max order, we're looking for N, aren't we? N lambda equals D sine 90. We go for 90 degrees. Sine 90 is 1. Therefore, N is going to be equal to D divided by lambda. And that gives us 3.5. So actually, third order is going to be made. So C isn't right. What about D real quick? If we had more lines per meter, so more lines per meter means that D has gone down. Could it produce more orders? No, it couldn't. Because we know if we have a smaller grating spacing, then we're going to have more diffraction. So all of our angles are going to be bigger. So no, that's going to be wrong as well. Electron collides with an atom and it's ionized. What do we have afterwards? Electron and excited atom. Well, it can't be that because we know we have an ion if it's being ionized. So it can't be an atom. Oh my word. Well, C's the only one that has ion in, isn't it? D also has atoms. So that's crazy. So it has to be C. Nice and easy. 19. So we have a 6 Newton and 10 Newton forces. What could not be the resultant force? Well, whenever it comes to thinking about maximum and minimum, we just think, right, what if they're in the opposite directions? And what if they're in the same direction? And then we can have them at any angle in between. So the minimum we can have is 4 newtons if they're counteracting each other. And the maximum we can have is 16 newtons. So the only one that we can't have is 3 newtons. So therefore, it's going to be D. Okay, 20, we're changing a tire, it looks like. We're looking for the minimum length needed to loosen the nut. Basically, we are comparing moments. So the moment for X has to be 200 times 0.8. So that gives us 160 Newton meters. Y, we're looking for the same, but we have a couple. So we can say that the couple, or the moment of a couple, is equal to one of the forces times the distance in between them. Basically, it's just 2 lots of one of the moments. So therefore, we can say that 500 times L is equal to 160. Therefore, L is equal to 160 divided by 500. And that gives us 0.32 meters. So it is B. Okay, ball bearing, we have a speed U. Oh, great. Okay, what are we looking at here? So this one goes straight up. This one goes over there at 30 degrees. That's at 2U. That's at U. Okay, so which is correct? A, Y's horizontal velocity. Well, we know that horizontal velocity has to be equal to 2U cos 30. Cos 30 is not half, so therefore it can't be that one. B, maximum height is half that reached by X. Well, let's have a think about this. What's the vertical velocity for X? That's going to be 2U sine 30. If you don't know where I'm getting that cos and sine from, have a look at my easy vectors trick video. Sine 30 is a half, so therefore it's going to be U going upwards. So no, it can't be that either. They're going to reach the same height. Okay, let's keep going. C, do they reach the ground at the same time? Yes, they do, because we've just found that they have the same vertical velocity going upwards to begin with, so it has to be that they're going to reach the ground at the same time. Let's just check D. Well, C and D are opposite to each other, so actually that should tell you that only one of them has to be correct, so it can't be A or B just from that. So relationship between Y and X. What is Y? It's the distance, so we can say that that is S. They're just trying to confuse us by using different letters. And X is time. So therefore, how are these proportional to each other? Well, let's think about our Suvat equations. If it's just dropped, then we know that we can use the equation S equals ut plus half at squared. It's just dropped, so ut disappears. But we also know that it's accelerating at a constant rate. So therefore, we can say that S is proportional to t squared. So that means Y is proportional to x squared. So it has to be A. We have a force of 500 newtons. We have a constant speed of 72 kilometers per hour. Let's turn that into meters per second, shall we? So we times by 1,000 and then divide by 3,600. So in other words, just divide by 3.6. And it gives us a nice 20 meters per second. That's nice. What are we being asked to find? We're being asked to find work done. Work done, as we know, is equal to force times distance. So therefore, that's going to be equal to 500 times the distance that it goes in 5 minutes. So there's going to be 20 meters per second times by 5 minutes and then 60 seconds in each. So what's that? 500 times 20 times 300. So I reckon it's going to be B or C. So that's 10,000 times 300, or in other words, 1 times 10 to the 4 times 3 times 10 to the 2. You can already see that it has to be A because that's the only one that has a 3 in. 24, this one confuses people a lot. So it's all about forces. So let's have a think about the tension in the spring. It's holding up 3 kilograms. So therefore the tension is going to be equal to 3G. But as soon as we cut this, what's going to happen to the 1 kilogram? Well, it has 3G pulling it upwards the moment that you cut it, but it's still got the 1G pulling downwards. So therefore, that one's going to be 2G. What about the bottom one? Well, it's just falling through free fall. Therefore, we know that it's just going to have that 1G. Therefore, the answer has to be C. Oh, great. Another one of these. So we're falling freely. What is its velocity after distance? Great. So we have a distance, so that's S. We want to find final velocity. So basically we're just being asked what is the relationship between S and V. So which equation are we going to use? Let's use V squared equals U squared plus 2AS. Drop from rest, therefore that's the case. So we can say V squared is proportional to S. But we're looking for what's happened to its velocity. So therefore we're going to say V is proportional to square root of S. And so therefore, well, they use D instead of S. But if that's gone up by times 2, then that means that velocity has gone up by root 2. Therefore, the answer has to be D. We have an input power of 100 watts, raises a mass of 10 kilograms, steady speed of 0.5 meters per second. The efficiency, well, first thing we need to do is find out the mechanical power. And that's equal to force times velocity. So that's mg times the speed. So that's 10 times, we're just going to say 10 because, like we said, we don't have to be super accurate. So that's going to be 50 watts. So we're using 50 watts, but we have 100 watts going in. Therefore, it's going to be 50% efficient. It's C. We have a velocity time graph. We're being asked what's happening to the force. Well, we can see that it is speeding up. At the top, we must have a decreasing force. And it's accelerating fast as here, so we have a max force in the middle. So it's going to be this one here. It's A. Another way of thinking about that is that force is proportional to acceleration. So we could think about the gradient, isn't it? The gradient gives you the acceleration, and so it gives you basically what's going on with the force as well. What is evidence that light is a transverse wave? A, they can be made to interfere. No, because sound waves can interfere as well. What about B? Not really. Diffraction can happen to sound waves too, but are longitudinal. C, yes, of course. Longitudinal waves can't be polarized. D, no, that happens for sound waves too. All right, circular motion. So we have a mass pulling downwards. So we know the force due to that is big mg. That's providing the force necessary to keep it going in a circle. So that's equal to the centripetal force. What are we being asked to find? M, nice and easy. Just mv squared over gr. Therefore, the answer is C. Frequency of a thing undergoing SHM is doubled. Amplitude stays the same. What else is doubled? Well, we know it can't be time period because they're reciprocals of each other. It would have to halve. B, total energy. Well, we know total energy is the same as maximum kinetic energy. So that's equal to half m Vmax squared. Vmax is equal to 2 pi Fa. So therefore, well, no, because if frequency is doubling, then that means the Vmax is doubling, so this goes up by a factor of 4. So no, it's not B either. C, max velocity. Yes, because we've just seen that. Max velocity is equal to 2 pi Fa. So that is the right answer. Acceleration, well, no, because we know that acceleration is equal to minus 2 pi f squared. And so if this is doubling, then again, acceleration is going up by a factor of 4. Finally, what's going on with the acceleration? Is it opposite to the velocity? No, that doesn't make any sense, does it? We know acceleration is always opposite to displacement. B, does it decrease as potential energy increases? Well, no, because at the top we have maximum acceleration, maximum force, so therefore it can't be that either. Is it proportional to the frequency? Well, like we saw over here, no, it's not proportional to the frequency, but rather frequency squared, so it can't be that, so it must be D, but let's just check it. Is least when the speed is greatest? Yes, that is at the bottom. At equilibrium, no acceleration, but we have the greatest speed. Hope you found that helpful, folks. If you did, please leave a like and click on the card and it'll take you to all the other papers in the playlist for AQA. See you next time.